So, we have seen that by simple logic we can say that the flow field in a doubly connected region can be determined uniquely if we know or if we specify the cyclic constant, and as before if we know the normal component of the velocity on all the boundaries or the potential on the all boundaries or a combination of the two. So, one additional constant is required, additional constant has come, that the cyclic constant has to be specified. This of course, we saw from simple logic, but let us check it with mathematics also, mathematical analysis. As let us first of all consider the single or doubly connected region. Think about this barrier. Okay. As before, this is A1 with normal N1, A2 with normal N2, and this barrier with normal N. As before, in this region now, in this domain now, we can apply that result which we had earlier. For a singly connected domain also we use this result. Remember, this V does not include this barrier, this is the boundary of that volume. Okay. And this now we can apply to this, applying that Gauss theorem by which we get it over the surface. And this area in this case is as before. These two are the integration on the two sides of the barrier. Okay. This is a doubly connected region. So, phi is many valued and the difference between the potential phi at 2 points on the two sides of this barrier is phi plus phi minus. On one side it is phi plus, on the other side the value is phi minus. and how much this will be? This integration is 0. Now, as before, let us consider again two solution. So, before that we can combine these two and we can make it like this. Which term we wrote first? 2 phi 2 v 2 into dA sorry plus kappa into where the cyclic constant is the difference in potential at that on the two sides, that is what is the cyclic constant. Let us now consider two solutions. Let us now consider two solutions. Phi 1 which is associated with velocity field V 1 and cyclic constant kappa, and phi 2 which is associated with the velocity field V 2 and let us say kappa 2. Then which is associated with the velocity field V 1 minus V 2 and cyclic constant kappa 1 minus kappa 2. we have little difficulties in the notations. Phi 1, phi 2 we have already associated with two surfaces. We have associated with two surfaces. What to do? Yes, unnecessarily we have made it. It was not necessary to write as phi 2 v 2. This is phi v n on it. Should you make this? There is no necessity, because it is integrated over the area A 2, integrated over the surface A 2. It was not necessary to write phi v n here. Yeah, n 1 and n 2 will be there. N 1 and n 2 will be there, but this we need not associate phi 1 phi 2 there. They are simply phi and v. N 1 and n 2 should be there, they are normal specified to that, to the two surfaces. So, this will be and similarly the other terms. Similarly, the other terms and and writing this we see that or write it now once again that if the solution has to be unique, if the solution has to be unique, then this v 1 minus v 2 must be 0, that is the left hand side must be 0 for unique solution. And how will that left hand side will become 0? If either V 2 minus V 1 dot A n equal to 0 on A 2 and A 1 or phi 2 minus phi equal to 0, both must be on A 1 and A 2 on the surfaces. This of course, this is the same condition which we had for singly connected domain, and this is the extra. And condition 2 have already explicitly stated. Phi is specified in all boundaries or remember about this third, the combination of A and B. It is always that you do not need both at the same part, any one on one part and the other on the other part, not on the same part. That is, on one portion of the boundary, if you know both, that is of hardly any use. Knowing one of these on one portion and the other on the remaining portion, that is what is required, such that you know everything, you know either of the two on the all boundaries. That is what is the requirement. Either of these two must be known at each and everywhere on the boundary surface. And also this, in case of a flow in a multiply connected region, that cyclic constant is also an additional factor that you must know. If the region is n-ply connected, then there are n number of cyclic constant, what we have mentioned earlier. So, for flow or solenoidal irrotational flow, you need n number of cyclic constant. Okay. That is, if you have a solenoidal irrotational flow in n-ply connected region, to determine that flow you must know n number of cyclic constant and these, either the normal velocity or the potential or a combination of the two on the entire boundary. So, these are the things must be specified, only then you will be able to get the unique solution is mathematical possible. Mathematically it is possible to get the unique solution for a given solenoid or irrotational flow field. Let us consider this type of a two dimensional, a special property of two dimensional solenoidal irrotational flow field. A two dimensional, a general case solenoidal irrotational flow field. For a two dimensional irrotational flow field, we have seen that the velocity is gradient of potential. Okay. For irrotational flow field, so for two dimensional flow, then what becomes? We have the, let us consider the straightforward Cartesian coordinate system, then we have V x, the x component of the velocity is d phi dx, and remember that phi is in general function of x, y and t in this case, let us say x, y, z, t, and V y is we have seen that in general for any solenoidal flow field, it is not necessarily irrotational. For any solenoidal flow field, we can define a stream function. Any two dimensional solenoidal flow field, we can define a stream function, it is not necessarily to be irrotational. The potential function can be defined only if the flow field is irrotational, otherwise not. But the stream function can be defined if the flow field is two dimensional and solenoidal, but not for three dimension. This potential function can be defined for three dimensional flow. The stream function is not valid, or the scalar stream function is not valid for three dimensional flow. You have to go for then a vector function. So, for 2D solenoidal flow, we have seen the x component of velocity, again let us say this x component of velocity is if we combine the two, then we get the result which is applicable for two dimensional solenoidal irrotational flow. These results are for two dimensional solenoidal flow, this is the result for irrotational flow. So, the combined result is for two dimensional solenoidal irrotational flow. Two dimensional solenoidal and irrotational flow what are the solenoidal and irrotational flow? That is the flow field in which there is no rate of expansion is 0 and the vorticity is 0. we have what d phi dx is equal to d psi dy and d phi dy equal to so, these two functions, the two dimensional potential function and the stream function, they satisfy this relation in a solenoidal irrotational flow field. Have you ever come across this relation or this type of relation? What is that? Where? Do not think in terms of this velocity potential or stream function, flow stream function, just think in terms of mathematical function. Phi is a function and psi is also a function. Yes, how did you come across this relation? Or you may think in terms of phi and psi, you can replace them by f and g or anything you like, or f1, f2. Linear equations? Huh? Exact differential. Anything else? You have come across this relation in your complex analysis, or you have called this relation to be Cauchy-Riemann equation or Cauchy-Riemann conditions. If z is a complex number defined by x plus I y, then a complex function phi plus I psi, and if the real and imaginary part of the functions satisfy these relations, they are called the Cauchy-Riemann conditions, and the function is called analytic function. The function is called analytic function. So, you see that for the potential function and stream function in two dimensional solenoidal irrotational flow field satisfies a relation such that phi plus I psi, which we may call a complex potential, is an analytic function of the argument z, which is x plus I y. So, that condition is that phi and psi we will call this as complex potential. This is the property of the analytic functions, that the derivative of this function is path independent. The derivative of the function is path independent. This I hope you remember, that is delta z you can take in any direction to find the derivative of this f z with respect to z. You can take delta z in any direction, the result will be the same. So, your z direction or the change in z may be only along the x or only along the y or any other direction, the derivative will be same. That is what is an analytic function. That is df dz is path independent. The real and imaginary part of an analytic function are also called conjugate to each other, meaning they are orthogonal to each other. That is, phi and psi are orthogonal to each other. You will be able to appreciate the idea better in this way. Instead of the two functions being orthogonal, okay, the functions are also called orthogonal. But you will appreciate it this way. Think about psi equal to constant. What is psi equal to constant? We have already seen psi equal to constant is a streamline. In a two dimensional flow field, psi equal to constant represent a streamline. Similarly, phi equal to constant will represent an equipotential line on which potential is same. And when you say that these two functions are conjugate, the stream function and the potential function in two dimensional flow field is conjugate or orthogonal, means that this equipotential line and stream line, they will intersect each other at right angles. Whenever they will intersect at right angle. In this relation, this phi x y psi x y, what we have written, we have not written any t, but in general they may be function of time. In general, this both phi and psi may be function of time. And the real and imaginary part, of this complex potential or real and imaginary part of any analytic function, in general, real and imaginary part of any analytic function satisfies the Laplace equation. Both the real part and imaginary part of any analytic function satisfies Laplace equation. And you see that as a result, what happened? If you have an analytic function, then it real part will represent a potential and the imaginary part will represent a stream function in any general 2 dimensional irrotational solenoidal flow field. Any analytic function think of, if you have just an analytic function, its real and imaginary part will be a potential function and a stream function. Whether it matches to a particular flow or not, that is a different matter, but it will satisfy both of these, the real part and the imaginary part will satisfy the Laplace equation independently. So, and if f represents a complex potential, so does I f. Okay. If f represents a complex potential, so does I f. We have already obtained the velocity, potential and stream function for one particular flow. Some other flows also you can write them now, but at least for one we have already written the potential function as well as the stream function, that is flow due to an infinite line vortex or a 2 dimensional point. Infinite line is 2 dimensional point. So, for we have already written the potential function and stream function for a 2 dimensional point vortex. Okay. So, now we can write the complex potential for that. Let us write the complex potential for infinite line vortex, that is a 2 dimensional point vortex. See how much it will be. We have already written phi and psi for this. So, find what is this complex potential f. The potential function was gamma by 2 pi theta and the stream function was minus gamma by 2 pi log that distance. If we consider 2 dimensional, then it is straight away r. Then add it phi plus I psi. Make it how much it is phi plus I psi. Phi is gamma by 2 pi theta and minus I gamma by 2 pi log r. Then what it becomes? Take out I gamma by 2 pi or say minus I gamma by 2 pi. From both the terms, take out minus I gamma by 2 pi. Then what happens? Log r minus or plus? F z is minus I gamma by 2 pi plus I square is minus 1 and what is this? Log r plus I theta. R e to the power I theta, log of r e to the power I theta. What is r e to the power I theta? Is z x plus I y. So, this becomes one more very simple flow which is both irrotational and solenoidal. I will tell you and tell me what would be the complex potential. A uniform stream along x, a uniform stream along x, a uniform stream with speed u infinity or say capital U, whatever you like, a uniform stream with speed u infinity along x what will be the complex potential? A uniform velocity, we will call it uniform stream. Okay, first of all, what will be phi? What will be phi? D phi dx is u infinity, d phi dy equal to 0. What is phi? Just pure constant we will drop, because that just a pure constant does not mean anything as far as phi is concerned. If there is a, if we go on adding any constant, it hardly matters, because see our main interest is the velocity field. Okay. So, if there is some unknown constant associated with the phi, it hardly matters, because when you take the gradient, that constant will vanish. So, just a pure constant has no meaning, we will always drop it. When we said the solution is unique, see that is again there might be a difference in constant, additive constant, that hardly matters. So, phi is u infinity x. What is psi? Sorry, plus or minus? Plus or minus psi? Plus. Sure? D psi dx equal to 0, d psi dy equal to u infinity, and the complex potential is phi plus I psi u infinity z. Now, let us see what happened if we differentiate this complex potential phi f. Now, as before we have mentioned that since f is analytic, the differentiation is path independent. Okay. So, when we differentiate with respect to z, we take the consider change only along x, it hardly matters. Then what it will be? D phi df dz can be written as simply d phi dx plus I d psi dx, because it is path independent. And what it is? D phi dx is V x and d psi dx is minus b y. So, this becomes V x minus v y. As a check, we can also think that instead of taking the change along x direction, let us take the change along y direction. That also can be done. If we consider change along y direction, then z is I delta y. Okay. The z is I delta y. So, if we consider change along y direction, then the derivatives will be 1 by I d phi dy plus I get cancelled. What is this? d phi dy is v y, y component, 1 by I is minus I. So, you have got the same result. So, this is also another verification. Now, look, following the same notation that the gradient of the potential is taken as the velocity. Similarly, if we consider now the derivative of the complex potential as the complex velocity, then you see this complex velocity is not plus. If we have the velocity component v x and v y, you would say the complex velocity is v x plus I v y. That is the way we generally define any complex number. If we have the real and the imaginary part known, we say this plus I into the imaginary part, but here you see this is not plus, this is not v x plus I v y, it is v x minus I v y. So, if we call d phi, d f d z as complex velocity, which we may call and we will call it the complex velocity, then you remember this complex velocity is having minus here, not plus. If we call this as a complex velocity, okay, we will not go further into this complex or any analysis of these irrotational solenoidal flow field, because up to now we have seen this irrotational solenoidal flow as just a part of the flow. We have seen that the flow consists of flow which is associated with a specified rate of expansion plus a specified rate of vorticity plus this irrotational solenoidal flow. Okay. Though we have mentioned in the beginning while started discussion on this irrotational solenoidal flow, that there are many situations where the complete flow is irrotational solenoidal. There is no expansion, there is no rotation. But we have said that there are, we have not seen how is possible, when do they occur. So, before continuing this further, we will now try to see what are the conditions or when a flow can really be solenoidal or irrotational, at least approximately. Without going on just discussing irrotational and solenoidal flow, we would like to say that the flow in which we are interested. As a pure mathematics, we could have gone on discussing on this, but we would like to see that what are those flows, where these solutions are applicable, how we can have this type of situation, so that we can use these. This complex analysis is a very well developed mathematics, and if we can use it at least for 2 dimensional flow, we get a very good result, already known results which you can straight away use. But before that we must know that okay, the real flow field is solenoidal, irrotational, otherwise there is no point in going on doing it. So, now henceforth we will for some time we will try to see that what are those conditions or when a flow can be solenoidal or irrotational, or what they are mathematically. Okay, solenoidal, irrotational, all those vector properties we are talking about, but in reality what are they? In terms of say engineering sense, what type of flow can be called that? That is what we will try to see henceforth. And of course, to see that we have to consider some more things which we have not yet considered, that is how do the forces affect the fluid motion. So, subsequently for next few class we will be considering the dynamics of flow. Next few class means next all classes.